The purpose of this tutorial is to walk through the spring development livestock watering systems, gravity system spreadsheet for past practitioners. This spreadsheet was developed by NRCS, and we are able to use this to help us design gravity systems or spring developments. So we're going to go through two examples on the same farm. You probably remember this from either the watering systems training or another video. I'm using this example because we are gravity feeding water in this example from the water tank down to a frost-free hydrant. And then over here we have a spring development scenario where we're collecting water from the spring and then bringing it down to a tire trough. However, we will start with this here. Reason being that this spreadsheet is good for checking two different aspects of a gravity system. One of which, checking that the pipe size is large enough to supply the designed water demand for the animal numbers. Another reason being that we're checking that the pressure of the system does not exceed the selected material and that there is sufficient pressure to operate the system in the case that we may have a float valve at the end of the livestock pipeline into the water trough. So without further ado, we will get started here. Again, here's our scenario. Got this 2,000-gallon water tank at the top of the hill, and we are conveying water to the hydrant down here through the livestock pipeline, gravity fed. As you can see, we're going downhill. Start out by entering in your site-specific data. This site was in Cambria. Assisted by your designer initials can go in there. Track number, field number. Depending on your funding source for the project, that may or may not be relevant. So if not, then feel free to use those fields to enter in any site-specific or relevant data. So for this scenario, we had 25 cows, 25 calves, and we have obtained the water demand and consumption per animal per day in gallons off of the Penn State Extension livestock water demands chart. We're going with 15 gallons a day for the beef cattle and 5 gallons a day for the calves. And then we will go ahead and get started with entering in our elevations. So our elevation at the source. The existing ground at the proposed water tank is 1,700 feet. However, the source elevation that should be used in this spreadsheet should be the elevation at which that pipe goes through the water tank. That is our source elevation. So we have 1,700 feet existing ground elevation. We want some cover over top of that storage tank for frost protection. So we'll go down another 3 feet. And the 2,000-gallon water tank, we're probably looking at about 6 feet tall, give or take. So the bottom of that tank is going to be at 1691. We do not want to put that pipe at the very bottom of the tank there really shouldn't be any sedimentation or anything in this system, seeing as we're coming right from a pressure tank up to the storage tank. However, it's generally good practice to have that pipe enter the tank at a slightly higher elevation than the bottom of the tank. So let's say that our elevation that we are going to use at the source is 0.2 above the bottom of the tank. So we'll go with 1691.2. This is going to be trough 1 since there's only one on this system. Then our elevation at the trough. So we go down here. It is roughly 1562. There's 60, there's 62. And then the elevation at the trough for right here. It's also not necessarily the existing ground elevation. So figure on a 2-foot high hydrant, we're going to be at 1564. And our elevation head difference is automatically calculated here. That's 127.2. So then you move along to select your pipe material. In this case, we're going downhill, reasonable size herd here. We don't need a large pipe, so we'll stick with PE instead of the PVC. The size of the pipe, let's shoot for 1.5 inch diameter. So the next step is the inside pipe diameter. We are going to go over to this PE pipe tab to 1.5 inches. So average ID, that's average inside diameter, 1.734. And this is important because while PE pipe is called 1.5 inch or 1.5 inch pipe, the true inside diameter for our pipeline calculations here, we need to use the 1.734. So then we'll punch in our Hazen-Williams coefficient. And if you just hover over the red mark in the corner, you will see that 140 is the Hazen-Williams coefficient for PE pipe or polyethylene pipe. Pressure rating, generally speaking, we're at 160 PSI for PE pipe. Desired flow, we want about 5 gallons a minute. That's determined by our demand. Our distance for the pipe or pipe length, we had 1,055 feet. On our layout. So then we will go over here to this column for our fittings. So we have these charts here to show you which fitting corresponds with what it is called. So the inward projection, we are going to have a pipe go through the wall of the storage tank. So I'm going to go with inward projecting pipe. Do one of those. And then as we go down the water line, there are no other fittings up until you get to the 90-degree elbow underneath the hydrant. So now that we've entered in our fittings that will be factored into the friction loss equation used in the spreadsheet, we will come down here and continue entering in our inputs in these gray shaded cells. So we click velocity, and it automatically takes you to the PE tab. So we were at 34.4 gallons per minute. Here's our flow in GPM. Here's our pipe size, 1.5 or inch and a half. And we'll go down to 34 gallons per minute. And our velocity there is 4.61. And the pressure loss at that flow rate and our selected pipe diameter, 2.01, result in 2.21 psi of pressure loss, ultimately 33.86 psi at the trough. So the standpipe check here is to check that there is enough head pressure on the pipe inside of the storage tank to provide our target or desired flow rate to the hydrant. So like I said earlier, you don't want that pipe coming in at the very bottom of the tank, the outlet pipe to the trough. We want that slightly elevated to allow for any potential sedimentation. Not that there's really any anticipated in this system, because we're coming right off of a pressure tank straight into a storage tank. But in general, it's good practice to not have it right at the bottom of the tank. So that was why I bumped it up a couple tenths as our pipe outlet in the tank. So back over here, loading head on the outlet. We'll start with 6 feet. As I said earlier, 2,000 gallon storage tank might be about 6 feet tall. And then we'll go down to 2 feet, check that we still have enough. And as you can see, we're still looking at almost 51 gallons per minute with only 2 feet of head. So we'll go down to a half a foot. And just as a reminder here, we're no longer using the discharge Q in gallons per minute. We want to check this to the desired flow. Just to be clear, we only need to provide at most 5 gallons a minute to the hydrant. So we can bring this down even further. So let's say we only have a tenth of a foot or almost 2 inches of water above the outlet pipe right here. So what this is basically saying is the tank can essentially be not empty, but only need a half of a tenth of a foot of water above the outlet pipe. So we're good to go with that. One thing I did want to point out, however, was that this velocity is nearing 5 feet per second. These charts do a great job in shading out the flow rate and pipe size combinations that will result in over 4 feet per second of velocity, which, if you remember from the watering systems training, we want to keep all design velocities under 5 feet per second, because that can cause some unnecessary stress on fittings, and the pipe can lead to water hammer and things like that. So That's why these are highlighted here, and just something to be aware of. So now moving on to the spring development scenario on this project. Again, down here in this pasture, there's a spring that may be causing a little erosion there. They also could benefit from having a trough down there in that pasture. So decided to collect that spring water in a subsurface drain, perforated, enveloped in stone, and then convey that through a livestock pipeline to the trough with an overflow outside of the pasture close to a stream. Okay, so again, start off with our site information. Assisted by, that's your designer. Track number, field number, depending on the funding source, may or may not need those. If they're not necessary, then feel free to enter in any other relevant site-specific data that could be used for the project. So as a reminder, we had 25 cows, 25 calves. We went to the Penn State Extension water requirements chart for livestock and found that average consumption for a beef cow on a hot day is 15 gallons per day and 5 gallons for calves. That ends up with a total demand of 500 gallons per day. Then we'll flip back here to determine our elevations. I've got this profile pre-made here that we can use for the design spreadsheet. Here's our existing ground line right there. And here's our proposed pipeline. So we're about 1546 there. However, our elevation at source, that is going to be along the line where water is no longer being collected. So we're going to come down to the anti-seep collar, where it switches over from corrugated perforated pipe to solid PVC. Again, this may show that a little bit more clearly, but there's the anti-seep collar. There is our perforated collector drain up to there, and then that is where we switch over to the PVC supply line. So we are going to use this elevation right here. We will say that that's 1541. This is trough number 2. And then our elevation at the trough. Similar to pressure systems, we want the elevation that we need to get the water to, which is going to be a few inches below the top of the trough. It looks like top of the trough here is 1530. So we'll go down 0.2 to 1529.8. Type of pipe, going with PVC. Size of pipe, we've selected 4-inch. And then the inside pipe diameter, we're on PVC pipe. Going to go to the PVC tab. And on here, we've got 4-inch pipe, and take that inside diameter of 4.134 and hover over the cells that have a little red marker in the corner. Hazen-Williams coefficient here for PVC pipe is 150. Pressure rating 200 is pretty typical for 4-inch PVC pipe. The desired flow rate, that is going to be roughly 5 gallons a minute. And then our pipe length, we're going to take my measuring tool, check the scale. We're at 150. So we need a pipe length, which is going to be 53 plus 5. So we have 58. No need to add the length of the subsurface drain. Our calculations, again, begin where the water collection ends in the pipeline at the anti-seep collars. So then we're going to enter in our pipe fittings, similar to the pressure system design spreadsheet. Let's go over to our tab to see what we may have. I'm going to punch in bell mouth for the fitting going from perforated pipe to solid PVC. We will then have an elbow going up, coming down the line. Our elbow is coming down, and it's right there up into the trough. And then we'll have another elbow right here for the outlet pipe, a valve at the shutoff valve location, and that is it for fittings. So we have 2 elbows and 1 gate valve. So now that we've punched in now that we've entered in our fittings, which will help calculate the total friction loss in this system, we'll go over to continue on entering our data in these gray shaded cells. But before we do that, I will point out that for this scenario, so for larger pipe, when using this spreadsheet, we are going to use the desired flow rate, because if you use this discharge Q, 365.6 gallons per minute, we're never going to collect that much water out of this spring. Hopefully not, at least. That is just telling us that that's what a 4-inch pipe can actually convey given our inputs, our head pressure, our friction loss, and whatnot. But we're not actually using that value in our calculation. Again, that's just telling us what that pipe can convey to the trough. And we use 4-inch pipe because that is the most standard size pipe for collecting spring water in a spring development situation like we have here. So we're going to move along to the velocity. For PVC, we've got 4-inch here, and we're going to use 5 gallons per minute. And as we go over here, it's minuscule, so it's not on this chart, but in this case, we will move up to the next available velocity and pressure value. So we got 0.38 feet per second. And then pressure loss, again, we'll go take our 4-inch pipe, no value at 5 gallons per minute, so we'll just go up to 16. The next lowest available, that's 0.01 psi per 100 feet. So there's only 0.01 psi loss, and we have almost 5 psi at the trough, which is plenty fine. This system is just your standard, typical spring development gravity fed trough. So water's coming up in, filling up the trough until it gets to an outlet pipe elevation where it then drains out. All right, that concludes the spring development design spreadsheet.